All right, let's dive right in. Today we're going to talk about something pretty fundamental, something that answers the question of why you exist. Yeah, it's that big. Think about it for a second. What is all the stuff in the universe actually made of? The chair you're sitting on, the phone in your hand, even you. What are the absolute smallest building blocks? It sounds like a huge, complicated question, but the answer from particle physics is surprisingly simple. It turns out everything, and I mean everything, gets sorted into one of two giant families. It's like a great cosmic sorting hat for particles. And which family a particle belongs to? Well, that changes everything. So on one team, you've got the Fermions. These are the matter particles. And honestly, they're kind of antisocial. They need their personal space big time. They absolutely refuse to be in the same situation as another identical Fermion. Then you have the other team, the bosons. They carry forces, and they're the total opposite. They're the life of the party. They love to pile up and get into the exact same state. And this one little difference in personality, it makes all the difference in the universe.
Okay, so let's zoom in on those antisocial guys, the Fermions, because this one golden rule they live by, this obsession with personal space, is literally the reason our world is solid.
So if you want to get technical for a second, what makes a fermion is this thing called half-integer spin. Look, don't get bogged down in the name. All you need to know is that this property is what makes them so standoffish. It's the source code for their antisocial behavior.
And that brings us to the main event. It's a rule with a fancy name, the Pauli exclusion principle. But all it really says is this: you can't have two identical fermions in the exact same quantum state at the same time. Period. They're the ultimate individualists. Every single one has to have its own unique identity.
So who are these little individualists? Let's meet the Fermion family. If you think of the universe as being built from Legos, these are the actual bricks. And they come in a couple of main types.
First up, you've got your elementary fermions. These are the bedrock. You can't slice them into anything smaller. This is where you find quarks, the things that build protons and neutrons, and leptons, like the good old electron that's zipping around every atom.
Now, these elementary guys can team up to form what we call composite fermions. And the rule for joining the club is super simple. You have to be made of an odd number of elementary fermions. So take a proton or a neutron. They're each made of 3 quarks. 3 is an odd number, right? So, boom, they are also fermions and have to play by that same personal space rule.
Okay, so we've met the players, we know the main rule. Now for the aha moment. This is where this weird, abstract quantum idea crashes right into our everyday lives and explains, well, everything solid.
So what's the big deal? What does this exclusion principle actually do? Why should you care that a bunch of tiny particles are antisocial?
Well, for starters, it's the reason matter is stable. That's a pretty big one. Without this rule, every electron in an atom would just collapse down into the same low-energy state. Atoms wouldn't have their structure, and the whole universe would just be a weird, formless mush.
And here it is. The reason you aren't falling through your chair right now is the Pauli exclusion principle. Seriously. The electrons in your atoms and the electrons in the chair's atoms are forbidden from being in the same state, so they push against each other. That resistance, that pushback, that's what we feel as solid. It's why you can't just walk through walls. It's a quantum standoff.
But just when you think you've got it figured out, the quantum world throws a curveball. What happens if you can trick these antisocial fermions into pairing up? Because under really extreme conditions, it turns out they can kind of break their own rules.
When it gets incredibly cold, 2 fermions, say 2 electrons, can form this little team called a Cooper pair. Now think about it. This new particle is made of 2 fermions. 2 is an even number, so it doesn't have to follow the fermion rule anymore. It gets to act like a boson, one of those social particles that loves to clump together.
And this little loophole has mind-blowing results. When electrons team up like this and start acting like bosons, they can suddenly flow through material with absolutely zero resistance. And that, right there, is the secret behind superconductivity, one of the wildest and most powerful effects in all of physics.
It just goes to show you how wonderfully complex this all is, right? We love to put things in neat boxes. These are matter particles. Those are force particles. But when you look closely, you see the lines start to blur. The universe is a lot more connected and, well, weirder than it seems.
So, let's leave it with this thought. The very same rule that makes your desk solid
can be bent to create something as wild as a superconductor. And if a rule that fundamental can be flexible, it just makes you wonder, doesn't it? What other quantum weirdness is out there, just under the surface, quietly shaping everything we see and touch every single day?